Okay, so now we'll talk about problem 3. So this is the one where we have a 3, 4, 5 triangle and a 6 by 7 rectangle, and both of them are cut into two pieces, a right triangle and a trapezoid. And the question is that the two triangles and the two trapezoids are similar, so they're asking for the smallest possible area of the triangle that comes in the dissection of the 3, 4, 5 triangle. So there are actually 4 different ways we can think about this. So the triangle that we cut from the 3, 4, 5 can either be, this side can be parallel to the 3 or it can be parallel to the 4. So if we cut like this, then in our rectangle, we can build this triangle off of the 6 side or off of the 7 side. So that leads us to 4 different possible cases. So we'll consider each case separately, because we're trying to find the smallest possible value of something, so we need to look at every case. So we'll start by looking at the case where this side is parallel to the 3, and then we make our triangle on the 6.
Let's mark the angles, which one is equal to which.
Yeah.
Let's help us to see.
So here, this angle is equal to this one.
Okay.
This is 3 to 4, and then this angle is equal to this angle. So luckily they both add up to 180. It's a good sign. And so this triangle here is 3, 4, 5. That means that this segment has length, what is it, 9 over 4? No, it's not 9 over 4. This is
4.5.
9 over 2, yeah. And since this whole thing is 7, that means that this part is 5 over 2. So that means that the ratio from here to here is 7 to 5 over 2. Right, so if we look back at our triangle, this part that we're looking for is, I'll just call it like a over 3 equals
7 over.
Yeah, that is
5 over 2 over 7.
5 halves over 7. Right, so that gives us that a is 15 over 14. Right? And then we can find the area of this if we just find this part using the similar triangle.
Everything is proportional. We can wait later because we can check all the triangles and see which one we want, right?
So we don't need to actually calculate the area.
Mm-hmm.
All right, so now let's look at this case. This time we're still building our triangle off the 6 side, but we're looking at a different kind of triangle. So this one is parallel to the 4. So that means that they're going to be 3 to 4 in this ratio. And if we do that,
Okay, can you mark the angles? Help me to see which one is which.
So these two small angles are the same. And then we run into a problem because this is actually 8, which is longer than 7. So the triangle is not even going to fit inside our rectangle. So this entire case is bad. So now let's look at this one. Again, we take our triangle parallel to 3, and this time we build it on the 7. So our angles are, this angle equals this one, and this one equals this small angle here. Or it's not a small angle, but it's a small amount of space. So again, we can do the same thing. Since this is 3 to 4, this side must be 21 over 4. And then
which is less than 6.
Which is less than 6, that's good. This small part is 3/4. So now we can do a similar thing. We call this B. Then
B over 3.
B over 3 equals
3/4
over 6. So that means that B is
8.
yes.
So I know that one is clearly bigger. Right?
Yes. So without even calculating the areas, we know that this one's better. We still have one case left though. This time we're still building on the 7 and we're looking at this triangle. So the ratio will be 3 to 4. And we can quickly see that this side is definitely going to be too big because it's 28 over 3. And that's way more than 6. So this case is also bad. So now we have these two possibilities. We're looking at this triangle and this triangle, and it's pretty clear which one has the smaller area because they're proportional, right? This one is base 3/8, so we're going to go with this. The height is going to be this 3/8, that's 1/2. So the area is 1/2 times 3/8 times 1/2, which is 3/32. So that's our answer.
But I still have a slight question about this, because the reason we solve this problem is basically we go with the ratio of these two sides is equal to the ratio of these two sides to get these 2/5, right? But that only talking about a pair of sides. But when we talk about the similarity of a quadrilateral, we actually need to talk about all pairs of sides, right? How do I know actually these two trapezoids are actually similar to each other? I do know the angles, they are fixed.
So then I
So
think,
this angle into 90, right?
and this angle, of course, is also fixed. So that means that, I think which means that if we just know the ratio of these two sides, then the complete shape of this quadrilateral is fixed. Because if we were just, I'm talking about the shape here, right? So we can change the scaling as much as we want. So to show that, suppose we can cut this into two parts, right? And set this part to be equal to 1.
Okay.
Since
by scaling,
shape, you can just scale it, right? And then call this part x and x.
So when that's 1, this is fixed. So let's call that C, a constant.
It's a constant,
And this is also
and this is also a constant, C1 and C2. The only variable here is x.
So you only have 1 degree of freedom.
And if we know the ratio of these two, that's x to x plus 1. If that's also fixed, that means x is unique. There's only about one value of x that satisfies that.
I see.
So that means that once we know the ratio of the top side to the bottom side, the entire quadrilateral shape is fixed. So that means that we don't even need to check the numbers, that they have to be the same.
That's very good. I would still check it.